Greetings, fellow nerds. I thought I would spend just a minute talking about how do we balance redox reactions. You should be like, what? We've covered redox reactions. Come on, Mr. Howard. I know we've done this before. Yeah, and most have. It's just when it comes to redox reactions, oxidation reduction reactions, we could encounter a wee little bit of a problem. Let me show you what I mean by that. So we're going to look at this reaction specifically. I love this reaction. So we have silver ions reacting with aluminum solid to form silver, elemental silver, and of course aluminum going into solution. Now, this is a redox reaction. We could tell if we did our oxidation numbers. Why don't we just take a moment to do that? We can see that silver ion is going from a +1 to a 0. And so notice, how does it go from +1 to 0? It's going down. It must be gaining -1s, right, to do that. So it's got to be my reduction. So we would say silver is being reduced. Obviously, if it's reduced, then aluminum is oxidized. But we could see that if we wrote out its oxidation numbers there, it's 0. Here it's +3. And so you can see that it's going from 0 to a +3. That's because it's if it's going up numerically, it must be losing -1s, losing negative charge or losing electrons. So it's obviously our oxidized person. So this is an oxidized, this is a oxidation reduction reaction. Great. But isn't it balanced? I mean, it smells like it's balanced. It's got one silver on the left and one silver on the right, one aluminum on the left, one aluminum on the right. So what we've learned about balancing is that this seems to be good to go, right? So balancing for elements. That has to be good to go. Turns out that there's one other thing that we have to now check for. This has always been in the background. It's just we haven't seen redox reactions until this point, so we haven't had to think about this. But this is extremely important. We have to also make sure we've balanced for charge as well. What does that even mean? That means that we need to watch out for electrons. I want you to notice that silver is gaining 1 electron. Okay, I just want that to kind of sink in for just a minute. The silver is gaining a single electron. But look at your aluminum. How many is aluminum losing? So it's losing 3. So if aluminum is losing 3 electrons, but silver's gaining only 1 electron, where are those other, the missing 2 electrons? Well, that's why this is actually not balanced. Remember, for it to be balanced, we have to abide and obey by the law of the conservation of mass. We can't destroy mass. We can't create mass. And so we are actually not balanced because we have 2 electrons that have magically disappeared. So how can we see that a little better? What we're going to do to balance all redox reactions, so here we go, is we're going to start by splitting these into their half reactions. So the oxidation go together and the reductions go together. Another way stated, all I'm going to do is look at this reaction and I'm going to put together who go together. So I know that the silver go together. And I know that the aluminum go together. And so I'm just going to write them on top of each other. Anytime you balance redox reactions, we're going to split it into half reactions, writing one on top of the other. Does it matter who we write first? Absolutely not. It is absolutely irrelevant. So we always start off by splitting into half reactions. Now what we're going to do is make sure that we are balanced for elements. What does that mean? It means that we have the same number of elements on the left and the right, as well as types. So notice that we only have 1 silver on the left, which is great. So we have 1 silver on the right, so we know this bad boy is balanced. We have 1 aluminum left, 1 aluminum right. We are now balanced. So that's pretty exciting stuff. But that being said, we now need to balance for charge. And to do that, what we're going to do is balance for charge in our half reactions. So here we go. I'm going to start by noticing that I've got silver going from a +1, and I'm going to rewrite those numbers up top here. So I've got a +1 here, going to a 0 here. How do we go from a +1 to a 0? Well, that must be because silver is gaining a -1. Another way stated, what we need is our charges to balance. So in order for our charges to actually balance, that we just need the sum of all of the charges on the left to equal the sum of all of the charges on the right. Let me write that out for you again, okay? So to balance for charge, what that means is we need the sum of all of the charges on the left, so to speak. That has to equal the sum of all charges on the right. Okay, so looking at this, I've got +1 on the left, I've got 0 on the right, and yeah, that's not balanced. So let's balance it. And the way that we can do that is if we add 1 electron here, because remember, electrons are -1, so -1 + 1 is 0. Let's do the bottom reaction. I've got a 0 up top here. So we're going from a 0 to a +3, and so we can add electrons accordingly. So adding, notice that we need 3 electrons on the right side. So hopefully you now have guessed it. The top equation is gaining electrons because it's on the reactant side. If you ever write electrons on the reactant side, that must mean it is gaining electrons, which means it's reduction. This doesn't matter, I'm just bringing this out real quick. And then of course, obviously, if we are oxidizing, we must be losing electrons, or electrons should be found on the product side, and so we can see them there. Okay, so I just thought I would bring that out for you, but notice that we are now balanced for elements, and we are now balanced for charge in our half reactions, but we don't have a balanced overall reaction. And to do that is pretty simple. All we're gonna do now is add the 2 half reactions together. To add them together, though, there's one major thing that we have to look at. Before we get to just add the 2 reactions together, we have to make sure that we have the same number of electrons on the left and the right. And right now we don't. So notice that we have a total of 3 electrons there, but only 1 there. So what I'm going to do is think about the 2 numbers, 1 and 3. What is our least common multiple? Well, it's obviously 3. And so what I'm going to do is go through and multiply every single thing in my top reaction by 3. So everything in this top reaction here, I'm going to multiply it by 3. Why? Because that gives me my 3 electrons that I need. But to get that 3 electrons that I need, every species in that top reaction has to also be multiplied by 3. So if you've done it right, here we go. So when we add our reactions together, to be clear, we add everything that is a reactant together. So everything on the left, on both half reactions, gets just added together, and then everything on the right in both half reactions get added together. So it's pretty easy to do this. So here we go, starting with the top reaction. And again, it doesn't matter the order that you write this. Here we go. I'm going to scroll down, give me a little more room. So we now have 3 times 1, so that's just 3 electrons, plus, well, remember we have to distribute that 3 to that silver ion as well, so that's 3 Ag+. Now I'm going to go down to my other half reaction because I have to add in it. So we didn't do anything to it, so it's just 1 aluminum. I'm going to move back to my top reaction again. So that's, it looks like it's 1 silver, but remember we're multiplying everything by 3 there. So that's going to be 3 silver ions. And then moving back down to my bottom reaction, that would be just 1 aluminum ion. And then again, 3 electrons. So this is what it looks like if we've added everyone together. Now what we get to do is look through, scan this reaction. Anything that is the same on the left and the right, we get to cancel. And notice that we actually have that happening in this case. So you can see hopefully that we have 3 electrons, 3 electrons. Your electrons should always cancel, okay? I can't say that enough. Electrons must always cancel out. When you add the half reactions. Okay? And so they do, we're great. Is there anyone else that cancels? There will be times there will be multiple species that cancel. In this case, there aren't. And so now we can finally write the balanced redox reaction. So here we go. This balanced redox reaction would be 3Ag plus 1 aluminum to form 3Ag plus aluminum 3 plus. So that's it, students. That's our final answer. But I want to be clear. I want you to notice that this is still actually balanced for elements. 3 silver on the left, 3 silver on the right. 1 aluminum on the left, 1 aluminum on the right. It's just now this is also balanced for charge as well. So this is how we balance redox reactions. Take care.